Okay, thanks everyone for coming. Why don't we begin? Today's speaker is Dr. David Hathaway, and he received his Bachelor of Science in Astronomy from University of Massachusetts in Amherst, and then his Master of Science in Physics and PhD in Astrophysics from both from University of Colorado in Boulder. And then he was a postdoctoral fellow here at in NCAR through the ASP program from 1979 to 1981, and then he moved to Sunspot, New Mexico, where he was an assistant astronomer at the National Solar Observatory. Following that, in 1984, he moved to Huntsville, Alabama, where he was an astrophysicist at NASA's Marshall Space Flight Center and served as the head of the solar physics branch from 1996 to 2010. Then in 2014, he relocated to NASA Ames Research Center in Moffett Field, California, and then he retired in 2016, but still works on areas of interest as a casual employee at Stanford University. And his research interests include observing, modeling, and predicting the sunspot cycle, and understanding magnetohydrodynamics of the sun's interior and how it produces the sun's atmospheric features. And today he will present on hydrodynamic properties of the sun's giant cell flows.
Right. Thank you. Thank you for that very nice introduction I wrote.
You're very modest.
It is a pleasure to be here and see so many familiar faces. Both of my thesis advisors are here, and I owe my career to the two of them. They kept their fingers in it throughout much of it, and I appreciate them both. What I'm going to talk about today comes from a discovery Lisa and I made with a summer undergraduate in 2013. And I'll get into the details of that, of course, but it has to do with giant cell flows on the sun. And it's supposed to advance the slide. And it's not. That will. So to start out with acknowledgements, I've continued to collaborate with Lisa, and we've discussed a lot of what I'm going to present today over the last few months. I'm now, or have been working since 2016 with Sushant Mahajan. He's a graduate student at Georgia State, now has an office. Apparently he sits in Barbara Thompson's office at Goddard Space Flight Center. And he's in the process of writing his thesis, and again, the two of them have added a lot to this and what hopefully is going to be a collaborative paper in the near future. Just to define what I'm talking about, giant cells, giant, 100,000 kilometers across, so that's 3 times the size of a typical supergranule. Cellular, so these are non-axisymmetric flows. Long-lived, typically much more than a month, and they're flows. So, we see them in the way things are moving around on the surface of the sun, and in the interior of the sun. And I distinguish that from other magnetic or atmospheric features that may or may not be connected to these guys. So when I say giant cells, these are the guys I'm talking about. They have a long history. This is the brief version. 1968, George Simon and Nigel Weiss. This was shortly after supergranules were discovered and characterized. They suggested that there ought to be, in addition to granules and supergranules, even bigger cells that extended to the base of the convection zone. I think they gave the term giant cells to them. There was a lot of searches over the years with kind of fleeting, maybe yes, maybe no. 1996, wrote a paper with the Gong Nearly Steady Flows group on early results from Gong, and one thing we found in that was if we did Fourier transform in space of the patterns we saw on the sun and then correlated that in time, we could see that the large patterns rotated at about the Carrington rotation rate. So there was something there. And again, it was kind of a hint that something was there. That was followed 2 years later. Beck, Duval, and Phil Shearer in MDI data now rather than GONG also suggested that there were long-lived Doppler features that lasted, were rotating at the Carrington rate. So again, these were just hints that something's there. The first one that came up with anything that suggested more structure to it is Liesel, is that the way you pronounce his name? Lyle, Rast, and Tomre, who found that supergranules often tend to align themselves north-south as if they were being governed by larger flows. So this is the first time where, all right, now we're maybe getting some characteristics of these flows in there. Fast forward 9 years, 2013, Lisa and I had this summer research as an undergraduate student, and we told them we're going to go look for giant cells. and we tried a number of different things, and the thing that finally worked was doing local correlation tracking of supergranules, so Doppler features on the sun, local correlation tracking of that, and then accumulating those over full rotation of the sun, putting together a map where you can average at a given longitude and latitude over the 14 days that you see that longitude and latitude, and lo and behold, there were things that persisted from month to month. And so we wrote that in Science. They had a number of characteristics we noted then, that they were large, long-lived. The flows tended to be cyclonic and anticyclonic rather than diverging and converging, and you'd expect this from large flows that are governed by the sun's rotation. They had hemispheric differences in kinetic helicity. We have a proxy for the radial flow from the divergence. So if you correlate divergence with curl, there's hemispheric differences that are what you'd expect for the effects of rotation on these large flows. And then there were Reynolds stresses, in particular at high latitudes. There's an equatorward flux of angular momentum, which is what you need to maintain the sun's rapidly rotating equator. Shortly after that, Rick Bogart, Boulder, and Servani Basu, using ring diagram analysis, found virtually the same flows with one, when we talked, there was one significant difference that they said their flows were all shifted 90 degrees. They looked the same, but they were shifted 90 degrees. This is, whoops. Turns out in our science paper, we shifted them 90 degrees just to put the key feature in the middle of the plot so it was obvious. So anyway, given that explanation, they really did match up, and I'll show that later on. Just as to interject a personal thing into this history, 1975, Yuri and Peter sent me to Sac Peak as a summer student, and George Simon was my advisor. And George Simon told me my summer project was to look for giant cells. It's been a long trip. All right, why look for them? George Mallory, when talking about climbing Mount Everest, famously said, because it's there. And in some sense, you know, we often talk about why we do solar physics, you know, because of the societal impacts of solar activity and so forth. But deep down inside me, it's scientific curiosity. I just want to know. you know, there's this puzzle out there I would like to know. And so, you know, that's my main reason for looking for them, is that, you know, I would like to know whether they're there, if they are there, what they do, how they fit in with numerical simulation. So the next thing, this is a check on our numerical simulations of convection zone flows. And then for their, you know, from that, the role in driving and maintaining the sun's differential rotation and meridional circulation. And then finally for their role in structuring the sun's magnetic field, and from that, atmospheric features. So there's lots of good reasons, but for me, it's still the first one. I'm just scientifically curious and I want to know. All right, so to remind you, convective flows is observed at the surface. 2015, I wrote a paper with Thibaut Thiel, and Thibaut, raise your hand. Thibaut's a graduate student at CU, working on a PhD, unfortunately in aerospace engineering. He should finish late this year, I guess is the expectation. But he was an intern for a whole year, as I recall, right? And during that time, we analyzed the Doppler features on the surface of the sun, did a series of analyses to extract 3 different components of the flow, the radial flow velocity, which you see at discenter, but you don't at the limb. And then for the horizontal flows, the poloidal flows, which have divergence but no curl, and then the toroidal flows that have curl and no divergence. So we came up with 3 or 4 different analysis techniques that could separate these different flow components. And what we find is shown on the bottom here. The black line through here is the characteristic velocity is a function of wave number from these spherical harmonic analyses. And the way I get characteristic velocity is I get a power spectrum, which is a velocity squared per wave number. You multiply by wave number and take the square root. This is something Aki Nordlund introduced to me decades ago. And the nice thing is it gives you a characteristic velocity, a velocity at that size scale. And so what we find is that this rising spectrum with very weak flows at the low wave number end, rising up to a peak or a plateau here at supergranules at L of about 100, rising again to another peak up here at 3,000 or 4,000 representing granules. That's the basic spectrum, but we have the different components as well. So in red is the poloidal velocities. These are the flows that are diverging and converging. And for most of this Doppler velocity spectrum, it's dominated by that poloidal flow. The blue line is the toroidal flow. These are the flows that have curl but no divergence. They're weak at small wave numbers. At wave number about 30, they overtake, and at the wave number smaller than that, they dominate. And this is what you might expect from the large things being dominated by the effects of the sun's rotation. The radial component is weak throughout until you get up to about the granule size where the radial flows start to become comparable to the horizontal flows. So what we're going to talk about today is down on this, below this wave number of 30 where things become largely toroidal. The method we're going to use to detect them is the one that Lisa and Owen and I, after unsuccessfully trying about 3 other techniques, is that we're going to do local correlation tracking of Doppler features, call them supergranules. We have a window, I'll show you the window in a bit, that's about 2 supergranules across. Before you get to that, you have to remove a bunch of stuff from the Doppler signal. So this is the a Dopplergram as you get them from HMI. These are 722nd filtered Dopplergrams, so the P modes are gone. This is, the fact that I throw away the P modes. Back in the Gong days, they used to call me a bottom feeder because I was using the stuff that they were throwing away, and I was throwing away their stuff. But we have to remove the known signals: spacecraft motion, the solid body rotation, Carrington rotation. And then after that, we determine via analysis techniques the convective blue shift, which is due to the correlation between upflows and intensity in granules that looks like a blue shift at discenter that disappears or reverses as you go to the limb. Differential rotation, changes in rotation with latitude, and meridional flow. We remove those, do a long-term average, and we find this junk. So these are instrumental artifacts from within MDI. You see fringe patterns and so forth here. But this stays relatively constant. It does change a bit, but it's relatively constant until they change their focus. And we know when those times are. So we go through and remove that as well. We then take the data, remove all of that stuff, and then put it onto equi-rectangular maps. So these are maps that have constant spacing in both longitude and latitude. Map the data onto this, and again, the flows are largely horizontal, so the signal's weak at discenter, gets pretty strong as you get out towards the limb. And of course, on this mapping, near the limb, things are stretched out due to foreshortening. So this is the local correlation tracking method that we used in the Science article in 2013. We take a circular aperture that, first of all, we take the 4096 by 4096 pixel maps. smooth them with a Gaussian, and make them 512 by 512. We're looking at big stuff, so we don't need all those pixels. So at 512 by 512, this is a 21 pixel window. It's about the width of two supergranules near discenter at least. And you take that window, you look at another image 8 hours later and find out where do you get the strongest correlation for that. And from that offset, get a movement in longitude and a movement in latitude. The method we used back in 2013 was to do these maps at 8-hour time gaps, 16 and 24, every hour on the hour with this 21 pixel circular window, but we would oversample the pattern by making those measurements on a grid that was 256 by 256, which is greatly oversampling given the size of the window. Back then, we removed longitudinal averages. So if you average all of those velocities together, you get differential rotation and meridian flow. So we removed the average in longitude of that. Turns out there's a better way to do that. And then we averaged those velocity maps over Carrington rotation using the Carrington longitude and latitude given at the time of the observations. And again, I'll show that there's ways to improve on this as well. So recently we've made a number of improvements. Some of this came from stuff I was doing with Sushant. Some came as I started redoing it again, realizing that we could do better on some of these things. So the improvements are we've improved the local correlation tracking method, primarily by changing the size of the window as you go to higher latitude, so you're actually covering the same physical area on the surface of the sun, and then also properly changing the search area as you go to higher latitude, so you make sure that you are properly sampling the distribution of velocities. We have a new enhanced method for measuring fractional pixel shifts. That when you find the peak in the correlation, what we had done before was you take the peak and the adjacent two correlations on side to side, top and bottom, and you take the parabola that fits through those and you take the peak of that parabola. That works pretty good, but there are problems, as I'll show in a moment. And then finally, we measure the differential rotation of the pattern that we find. And then instead of using the actual longitudes from the maps, it says the Carrington longitude along the discenter is this. We use a longitude, when we're looking at things separated far away in time that include this differential rotation to put things in the proper place at the given time. And this gives us maps that are synchronic in that they represent a moment in time. So we make maps rather than a Carrington rotation at a time. Every day at the 0 hour at midnight, we make a new map. All right, so the method improvements. First, the one that I mentioned is changing the size or the shape of the window so that it covers the same area, so that you get a couple of supergranules across here. You go up here, it's still a couple of supergranules across, and then the search area up here gets wider as well. So it's computationally it's much more expensive, but the results are far, far better. The other problem, this is something Sushant noticed, was that even though we try our best to measure fractional pixel shifts, when in particular with magnetic data where the things are unresolved, there's a tendency to avoid half pixel shifts. And so what he did was make this histogram of values from our measurements. In this case, I think it was of the meridional flow, and you see these dips that are at half pixel shifts. You go to a 24-hour time gap, and again, there's these dips at half pixel shifts. So, we wanted to correct this. It turns out this is a problem seen in other communities. There's a fluid dynamics community that measures flows within the laboratory by shining light, a wall of light through a fluid, and they have little particles in there. It's particle velocimetry. And so they have the same problem we have with magnetic fields. They get tiny little features that move around, and they notice the same thing, that when the thing you're looking at is unresolved, you get this sort of problem. We solved it, and the solution was pretty simple. that when you do the cross correlation, you start off with an area, in one map, and then you try to find an area in another map. And you find, oh, it's like a half pixel shift off. And so what we do is take the original one and use an interpolator to shift it a half a pixel, and then do it again. And then we iterate until, you iterate like 3 times, and you get down to very accurate, a 20th of a pixel or so. And again, none of the avoiding half pixel shifts. So we've made those corrections. These are raw, the raw data from just correlating one map with another map. In this case, 4 hours later, 8 hours later, 16 hours later. The thing we've noticed here is data gets pretty ratty at 16 hours. And it's primarily 16 hours within this little window. The supergranules, the 2 supergranules you have in there have changed enough that it's pretty easy to find another little patch close by that matches even better to what you had originally. So this also shines light on what we did back in 2013, where we did 8, 16, and 24. I didn't even bother looking at 24 with this again. This is bad enough. We've done all of our stuff with this 4-hour time gaps now, because they're much cleaner. You can filter out this stuff by saying, if the velocity is above some unexpectedly large value, don't use it. But it's easier just to use this data at 4-hour time gaps. So to construct the maps, another change that we made was I told you before, when we got the maps, you have to remove the axisymmetric flows. And so what we removed before was just the average in longitude from these diagrams. Now that we have the actual, make the diagrams, it's like, oh, that's not really a very good approximation of what there is within that map. So what we do now is we remove this pattern of flows from each of those maps, since this is fixed in our field of view, and a lot of this strange stuff here comes from the nature of supergranules. If you imagine a supergranule just a little above the equator, as it moves across, as it gets near the equator, it looks like it rotates around, and then what was a red shift over here becomes a blue shift on the other side. So the whole pattern kind of rotates as it goes across. So we remove those and to construct our maps. And so to begin with, we then made maps in a similar way to what we did in 2013 by putting together these things based on the central meridian longitude and averaging over time. This is a comparison of those patterns that we get now with what Bogart, Boulder, and Basu did in their 2015 paper. So, whoops, now it works. Oh, I know why it didn't work. I was trying to go backwards when all I could do was go forwards. Here we go. So this is theirs from ring diagram analysis. This is ours from correlation tracking of the supergranules. And in particular, at high latitudes, you see one-to-one correspondence of things. We're seeing the same features. There's little doubt about it. Although, when you get to the low latitudes, and we'll get into this in a moment, when we get to the low latitudes, it's a little harder to see. And I think this was an early disappointment. People were hoping to see, Busa columns or banana cells lined up along the equator, and we don't really see that here. But certainly at high latitudes, we're seeing very much the same features. We've done cross-correlation of that pattern with itself 28 days later to get a rotation rate out of it. So this is the cross-correlation averaged over, I think, the full 8 years of the data set. It's a very good correlation of the pattern. The red is the peak, and even at the low latitudes, it's up around 0.2 or so, which is pretty good after 28 days. There's blue dots through here that are placed on the peaks of the correlation, and a white line that goes through the middle of that's a best fit. It's usually when people do differential rotation profile, it's a constant plus something that goes like sine squared latitude and something that goes like sine to the fourth. That's not enough. We have to go to sine to the sixth to actually properly capture that pattern. This is in blue what you get from that rotation profile. And you notice immediately there's this, it's not even flat, but nearly flat, nearly constant rotation rate between about plus and minus 30 degrees. So this equatorial region is moving almost rigidly, but at the Carrington rate, which are actually slower than the Carrington rate. And if you look from helioseismology within the sun at these latitudes, you never find that rotation rate. So that was a key early on, that there's something interesting going on here. The red line through here is the rotation profile that Lisa and I get from correlation tracking on the magnetic elements. Quite different, as far as where the peak is, and even at higher latitudes, there are significant differences between these profiles. Yes.
You've gone a bit quick for me here. Can you just remind me what that's a correlation of? Is it the rotational component of the velocities you spoke about at the beginning?
It's a correlation of this pattern with that pattern. So it's
what is that of? Is it of the component of the toroidal component of the field you mentioned at the beginning?
This is. I have longitudinal. These are longitudinal velocities here. I have longitudinal velocity and latitudinal velocity, and so that correlation is I correlate the longitudinal velocity from this map with 28 days later, and that's about what this is. Okay. And you get, and then but I also do latitudinal, and just add, what you see here is all of those correlations averaged together in this plot. They're all averaged together.
So this is all three components: the line of sight, the divergence, and the there's really no. We don't measure the radial flow. We're correlation tracking on the surface of the sun, so it's only horizontal motions that we measure. And as I showed in that plot that I did with Thibault earlier, there's virtually no radial flow at these sizes. Thank you. Sorry.
All right. So given that differential rotation profile, we now produce new maps where, given in this case the central meridian is at 164 degrees, we put the maps together by going to later and earlier days. Near the equator, since it's a 27-day rotation, you can go plus or minus 13 days, you get it all. At higher latitudes, it's a 35-day rotation. So you have to go longer in time to fill up everything in longitude. And so one difference you see between the old maps that didn't have differential rotation is that there are now features, away from that central meridian at 164 degrees that aren't in the other map, because you didn't allow those longitudes in. You only allowed plus or minus 13 days, and it takes longer than that to map the full sun. So you need to have these longer time intervals at higher latitudes. All right. Let's see. So. Yeah, that. Oh, I guess this is a comparison. So that I'm sorry. I jumped ahead. So this is one where, again, you see features in particular at high latitudes that creep in. And plus, it's a lot spottier over here. This is with 8-hour time gaps. This is with 4. So there's a number of improvements that come in making these maps compared to those. All right. So here's 8 years of these maps. The thing to notice is that there are 2 regimes. There's an equatorial band that hardly moves at all, and then these high latitude bands that are moving with differential rotation, and things are getting sheared out, as you watch. You see in particular at higher latitudes, they persist for months. There's a little thing moving across here that's basically, every rotation, as you see a little different latitudes. Again, there's two different regimes, and that's going to become really important here in a few minutes. You can also, from time to time, see active regions pop out through here. Even though we've got this fairly large window, the fact that we oversample, we can get active region flows. The characteristics we see in the active regions is that there's outflows on the leading edge and inflows on the trailing edge. I didn't go back to all the helioseismology that's done this to see whether it matches or not, but that's the nature of the signals we see, at least. Where are we at? 15. I'm going to jump ahead.
Point that out to us, please.
The what? The active regions?
No, the behavior you just described.
For active regions or the two different regimes? The active regions, occasionally you've got to wait for one to come in, and we're already getting late in the cycle. So again, 2017, there haven't been many active regions, especially good ones around. I'd have to back up, and you almost need to do a freeze frame of it. So the active regions, like it says, right now, this is at a phase of the cycle where they're small and hard to see in this.
David, when I look in the equatorial bands, it almost looks like there's a kind of a throbbing.
Yeah.
Is that due to temporal sampling, or is that actually something that's in the data?
It's something in the data. All right, so the kinematic properties here, as you would look down, I think at 30 degrees onto the sun, what these flows are like. You can see that they are largely cyclonic and anticyclonic. So again, this is what you'd expect from the effects of rotation on the flows. Blue is retrograde, and you see the blue things in the blue areas tend to be moving towards the poles. Things in the red areas tend to be moving towards the equator. So you can see here some of this Reynolds stress or transport of angular momentum that is needed to help maintain the sun's differential rotation. All right, so we've measured those quantities. So this is kinetic helicity, and again, we have a proxy for the radial velocity, which is the divergence of the flow. So this is the product of the divergence with the curl at every point, and then averaged over longitude and shown as a function of latitude here with 2 sigma error bars around it. And you see, again, two regimes where near the equator, there's this very rapid change from one hemisphere to the other with left-handed helicity in the north and right-handed helicity in the south. As you get to the higher latitudes, it kind of flattens out. This is the Reynolds stress, again with 2 sigma error bars. At high latitudes, it's equatorwards. It's positive in the north, negative in the south. Through the center, it's, if anything, it's zero, but it may be in the opposite sense, that it's a flux away from the equator rather than toward the equator. So I want to drive home once again that they're what we're seeing are 2 different regimes depending upon latitude. Yes.
So I see a asymmetry between the north and south. Is that kind of what you expect?
I guess it's not unexpected. I think on a long-term average you'd expect symmetry probably. This is over 8 years of up to now of HMI. I would think on a long-term average you'd expect symmetry. Short-term averages, yeah. And again, you can 2 sigma, even with 2 sigma errors, there's room to move things around here. All right, the meridional flow. Well, we can also, in addition to do the correlation and longitude, find out how do you have to move these strips to get the of the giant cell pattern to get the best correlation by moving it in latitude as well. This is the result over from 8 years, again with the average in the dark blue, the 2 sigma range in light blue. Here again, 2 regimes near the equator within plus or minus 30 or 40 degrees, no meridional flow. If anything, it's a meridional flow towards the equator. At higher latitudes, it's towards the poles, and it's rather significantly towards poles. This is 5 meters a second for these large things, and where they might be rooted in the convection zone. That's a pretty large poleward meridional flow that you see at high latitudes. And then this is the differential rotation profile, again with the 2 sigma errors on it. All right, we tried to find torsional oscillations in this by taking the rotation profile and averaging it over the 8 years and removing that 8-year average from each one. Lisa thought she could see things in here. I don't see much over here. Here with the magnetic stuff, you see the rapid rotating branches coming to the equator at about the time of maximum. Unfortunately, this cycle, we didn't have the polar spin-ups that we saw during previous cycles, so there's not an awful lot going up here. There's maybe a little bit of enhancement there. But over here, I don't know whether I see the pattern or not. Lisa thinks that, that might be something else. I'm not so sure. Differential rotation with depth. If we take what we measure for the differential rotation and assume that these things are being transported along by the flows they're embedded in, so at some depth, at low latitudes it simply doesn't work. This stuff simply doesn't work. That the blue dots here, they kind of lay on top of each other here. At 0 and 15, they're basically the same. And my pointer's dying. So at the surface, right at the surface, you kind of get a match. You get another match near the base of the convection zone. At 30 degrees, it doesn't match anywhere within the convection zone. As you go to higher latitudes, you get consistently, it's only at the base of the convection zone. So the only place you match that rotation rate is near the base of the convection zone. And so this is where the 5 meter a second poleward may come in. But again, the assumption is that these things are being carried along with the flows they're embedded in. And as I will show you soon, that may not be the case. So here's the meridional flow, and again, at high latitudes where 45, 60, we get up to 75 degrees. The rotation rate only matches at the base of the convection zone. The meridional flow is poleward at 5 meters a second. That's a pretty significant poleward flow to be at the base of the convection zone. And it's the wrong direction to what people would like it to be. As I was doing this last summer, this paper came out. Loptien and all of the Stanford guys that moved to Germany. Although Rick Bogart stayed behind. But one thing, what they did was local correlation tracking of granules. So they looked at the intensity pattern in HMI and did local correlation tracking much as we do. I think they even used a similar size window and did it with 30-minute time lags. One problem they have with granules is that you see them very nicely at discenter. You get away from discenter, they're hard to see. You get near the limbs, and in particular near the poles, it doesn't work at all. So most of their measurements were only near the equator. But they made similar maps to what we did along the equator, and then did a K-omega diagram. So you do a spherical harmonic transform, and look, in this case, at M equals L. So these are kind of the wings along the spherical harmonic transform, and do FFT in time, and I'm quite sure, given the size of their bins, they did 1024 time bins, and I'm assuming 1024 days, but it may have been a finer scale than that. I haven't gone back and looked in detail. But what they find is that there's this ridge of power, and you can pick out some of these out. L4 shows up pretty good, and boy, this thing's dying. L4 shows up pretty good. I think this is L of 8 that's really strong. At higher wave numbers, maybe this line isn't best, but this line is the line that you expect from Rossby waves. So Rossby waves have omega over 2 pi, that's basically twice the Carrington rate, which is 453 nanohertz, so right around 900 nanohertz, divided by m plus 1. And so that's the line going through here. And so their conclusion was that they were seeing Rossby waves in this pattern near the equator. And that would help to explain why I see, different regimes, a regime near the equator that seems to be doing one thing, pulsating perhaps, and then this high latitude one. And the high latitudes they don't see. So given this, I have to go and do it myself. So the first step is to do the spherical harmonic transform. And so here's the amplitudes of the coefficients, plus and minus m, L going up. The top is for vorticity. The bottom is for divergence. And the first thing you see is there's much more signal in the vorticity than the divergence. And that's as expected from these large scale things. Over here is the line plot showing that most of the signal is in the toroidal component, and the divergence, the poloidal component, is much weaker. So this is the first step, is to do the spherical harmonic transform, and then along the edges, along these edges, you then do a Fourier transform in time to get the temporal frequencies. I need to remind you, because I'm going to go off on a little bit of a tangent here, that when we do this cross correlation of the supergranule pattern, the longer the time lag, the deeper you look. And that's shown in the diagram on the left, that the red dots are from helioseismology. This is Jesper Sko's results showing through the surface shear layer the increase in rotation rate as it goes through the surface shear layer and under. The black dots through here are from doing taking an equatorial strip of the supergranules, the Doppler velocities, and along the equator there are east-west velocities, or all you see, north-south you don't. East-west velocities, and they get multiplied by the sine of the angle from discenter. So you've got to remove that projection, or you get spurious velocities. And so Jesper Sko came up with this idea of dividing by the sine of the longitude from discenter, or taking the sine of the longitude from discenter and dividing by the square root of the sine squared plus a little thing so it doesn't blow up right at zero. And so you can basically deproject the velocities, take a Fourier transform of them to get wavelength. And what I found was that the wavelengths, the rotation rate, you got the rotation frequency and the wavelengths matched up to what you get from helioseismology if the cells were being transported at depths equal to their widths. So like at 30 here, these are cells that have wavelengths of 30 megameters, and they have rotation rate that matches up at a depth of 30 megameters. Even without the projection effects, if you go to do the cross correlation, which is what I've been doing here, correlating with time lags, as you go to a longer and longer time lag, the small scale stuff no longer correlates. So you're seeing the big stuff as you go to longer time lags. And so there's a correlation here where as you go from short time lag to longer time lags, the supergranules you're following are rooted deeper and deeper. So you're sampling deeper layers within the surface shear layer. This is a long way to getting to this, which is with our 3 different time lags at 4 and 8 hours. At 4 and 8 hours, the toroidal components are almost the same. You start to see the poloidal component comes up, but I'm absolutely convinced that's noise that's starting to raise it. You go to 16-hour time lag, they agree down here, but then everything kind of blows up. When we wrote our science paper in 2013, we, I think, erroneously concluded that the flow velocities that we're measuring in the giant cells increased as you went inward, based on this power increasing inward. I no longer believe that. I think what we're seeing are flow velocities that are virtually the same at the depths that we're measuring at 4, 8, and 16 hours. And so through most of this surface shear layer, the flow velocities in the giant cells are about the same. The next step was to do the K omega diagram. This is ours, this is theirs. Again, I did 512-day bins, so our temporal frequency resolution is not quite as good as theirs, but we do better. I can not here, but I can pick out peaks down here at wave number 3 or so that still fit on that line. If instead of taking the strips along the wings of the diagram, the spherical harmonic thing, I take strips. Actually, let me go back. So instead of doing FFT in time from these, I'm going to do an FFT in time at L1, L2, L3, and so forth. So I'm taking vertical slices through that diagram and finding the temporal find the temporal signature, and what you see is very different diagrams. At m equals 1, it's the same frequency for all L's, but it's only the odd L's that you see it. So what this is telling me is that, first of all, this is the high latitude pattern. It also, the frequency that you get here, that's 90 nanohertz off of the 450, so that puts us somewhere down in here for rotation rate. So these are the high latitude modes that are coming in. The fact that you're only seeing that you're at odd M and odd L means they're symmetric across the equator. If we go to M equals 2, the frequency is almost, this frequency is almost double of that, but you got to divide by 2 to get how the pattern is moving. About 80 nanohertz off of the 453. So again, down in here, at 3, it's starting to get a little ratty, but again, similar thing. So I think here, with this, we're seeing the high latitude stuff that does appear that it's being transported bulkwise by the flow. It doesn't show the same, anywhere near the same sort of relationship between nu and m that you got from the Rossby wave type thing. All right, conclusions. And there's a bunch of them, and there's no way I can read it on here. So first of all, we've improved the local correlation tracking method. We get cleaner velocity data, and the differential rotation profile we get produces more complete velocity maps, in particular at higher latitudes. We actually get features that you couldn't have gotten because you needed to go more days, plus and minus, to fit them in. As before, the flows are largely toroidal. These are vortices rather than diverging and converging flows, with left-handed radial helicity in the north, right-handed radial helicity in the south. There's these two regimes, this high latitude spiral pattern. If we look down on the pole at this, it's wave number 1 near the pole, and it spirals out from the pole. So there's this spiral pattern at high latitudes. At low latitudes, and again, they persist for many months. At low latitudes, it's a wave-like pattern that has a somewhat shorter lifetime if I go by the strength of the correlation. The high latitude features transport angular momentum equatorward, and they drift poleward, and they have a rotation profile like that found at the base of the convection zone. The low latitude features, transfer angular momentum poleward, if at all. Again, if I take for the error bars as real, then yeah, there's poleward transport rather than equatorward. But it's almost consistent with none. The low latitude features have Rossby wave-like properties, and this still confused me a little bit. The properties are that the phase velocities are retrograde, the group velocities prograde, and yet when I do a correlation of the pattern, it's moving retrograde. That should be group velocity. So I still don't understand why the pattern is moving retrograde with respect to the layers it's in. Let's see, this poleward drift at high latitude suggests a meridional circulation with 2 cells stacked in radius, at least at high latitudes, where it's poleward at the surface, equatorward starting at the base of the surface shear layer, but extending into the interior, and then poleward again to make up for all that mass you're taking equatorward at the base of the convection zone. And so with that, this is my story as of today. I'm free to change it in the future. And I thank you all for your attention. Questions? Peter.
Could you go back to the video that you showed of the velocity vectors, sort of in the middle of the talk?
This. No, the ball. This.
Exactly. Now, have you looked at correlation or anti-correlation between equal latitudes, north and south hemispheres?
Look at what I see in the north and what I see at the south at the same latitudes.
You see patterns in one hemisphere, the same latitude that correlate.
I haven't specifically tried that, but when I did the K omega diagram for m equals 1, and it showed that what I was seeing at m equals 1 was symmetric north and south, suggests that they're in phase north and south. But I haven't done, and I should do exactly what you said. Look and see whether, and that's actually the previous movie. Is, when you see a blue strip up here, is it a blue strip down there? And you can't tell just by watching. You have to do as you said, actually go in and see how they're correlated north and south.
The reason I'm asking that is that the Rossby wave formula you're using applies to a thin spherical shell. The sun's convection zone is thick, not thin, and you have the possibility of these columns, okay? And the Rossby wave characteristics of those are quite different than if you were working in a thin spherical shell. You can go back to the early work, and they do have phase velocities, and they have Rossby wave-like characteristics, but maybe even the sign changes.
Okay, well again, the Rossby waves we only see near the equator. It's like within the tangent cylinder for the convection zone near the equator. And of course, the real problem with Rossby waves is they're gravity waves. They're gravity waves. The restoring force is gravity. You need a stably stratified media to make them do.
Sorry, that's off the mark.
Oh, really?
They're not restoring force in Rossby waves is rotation. Coriolis force is not gravity.
That's a balancing force between, but I may be wrong, but I still thought we see Rossby waves in the Earth's atmosphere, stably stratified.
But the classical Rossby wave formula, there's no gravity in it.
In it at all, really?
No.
Okay.
It may depend in some implicit way on the fact that the shell, the Earth's atmosphere, is stably stratified.
Yeah.
Okay. That's not the restoring force. The restoring force is the change in Coriolis force
With latitude, yeah. So it's the equatorial beta plane sort of thing.
Well, beta plane.
Yeah. Others?
Yeah. These high latitude spiral features. Now, if you look at synoptic magnetograms, and sometimes you have to crank the contrast up, you do see, features that kind of look like that. They're the trailing polarity that get kind of advected around. Is there any correlation?
No. Lisa and I have found with the surface flux transport, you make those patterns purely from surface flux transport. Differential rotation, diffusion, and meridional flow makes those patterns. If you try to correlate, and we did this before, I haven't done it with the new improvement, but we tried it back in 2013. Let's correlate, see if there's a correlation between these features and the magnetic features. There wasn't any. Junwei Zhao claimed at one point that he saw from similar flows from helioseismology, a correlation between polarity, magnetic polarity, and whether you're moving towards the polar of the equator. But I think he's withdrawn that. Phil at one point I remember at a AGU meeting, touted this as a new discovery, and then now he doesn't talk about it anymore. But yeah, no, that has come up before. I'm glad you asked it, because it has come up before. But you can reproduce those trailing spirals in magnetograms purely from the decay of active regions and surface flux transport.
Sure, so you're saying these flows are deeper down, they're not correlating with those surface flows in that way?
They're not correlated with the surface magnetism in that way. Again, what I tried to show, and it took me 3 or 4 slides, was that I think what we're seeing is basically the same velocity pattern through the surface shear layer at least. How much deeper than that this pattern persists, I can't say, but it looks like it wasn't changing in amplitude as we suggested previously, but about the same and the same pattern through the surface shear layer. You still got a long ways to go to the base of the convection zone. Yeah. Yuri?
David, you're deducing everything from correlation of supergranular patterns. A lot of other things going on. And so, have you any basis for suggesting that what you see should be deeper than supergranules extent?
That was, well, supergranules extent, that if you go to a longer time lag, I'm looking at bigger supergranules that extend deeper. That's why I went through that 3-slide thing about, size of supergranules and their rotation rate is a function of depth. But you're right in that we really only know, through the outer 3% or something of the sun. That's all we can say for now, is that we're seeing these features within that layer, but given in particular the rotation rate of this thing, that the only place you match that is near the base of the convection zone at the high latitudes. And when I do the k omega diagram for m equals 1, it's indicative of a pattern that's being advected. Everything, all different Legendre polynomials, but with m equals 1 are being advected at about the same rate.
I don't question that. But the question is, what is the sampling, and how deep does the sampling extend?
Okay, well, and the sampling extends from a depth of about 15 megameters to a depth of about 30.
30.
Yeah.
That's basically within the shear.
Oh yeah. It's right in the middle of the surface shear layer. But I've been trying to argue that since we don't see much change over that, and the fact that the rotation rate of the pattern doesn't match the surface shear layer at all. It's not even close for the surface shear layer. It's got to, that it's probably something that's rooted much deeper in the sun. Phil?
Yeah, I very much enjoyed your talk. I am, if you don't mind asking a couple of very, very elementary questions going back 100 years or so.
I'm not that old. I'm not that old. Neither is he, yes. Hey, we add them up, yeah, we could do that.
So it's about a couple of questions. First one is the supergranules are most clearly seen, and they weren't even discovered 60 years after the network was discovered. So
right.
You're talking about hydrodynamics, and so when you look at the network, it's clearly magnetic, and it's the supergranules are 30 megameters in size, something like this.
Yeah.
But the supergranules can't actually be a convective cell, because if we understand convection, you typically, a cell vertically is going to be a couple of pressure scale heights. That's much, much smaller than the depth of the diameter of a supergranule. So I'm asking the question, what is a supergranule, first of all?
I disagree with your saying they can't be convective. If you look at numerical simulations for convection, radiative hydrodynamics, starting at the surface and above and going in.
Okay, the surface layer is a different thing.
Well, what you find is that right near the surface, it's scale height. You see granules.
Right.
As you go deeper, the structures you see become larger and larger as you go deeper. And it's primarily because you're filtering out the small scale things. So there's a filtering with depth that takes out the small scale stuff, leaves you the big, but that big stuff still influences what's happening at the surface.
So if it were convection, wouldn't you expect the depth to be, say, in a couple of scale heights only? Because that's sort of what, I mean, these things are like pancakes at the surface. They're not a big cell that's
I disagree. I disagree.
Well, I wonder what the evidence
Yeah.
is for that. And then
Yeah.
the other question is, forget all the physics behind it. If what you're seeing is a real surface phenomenon, shouldn't it organize the magnetic field in the same qualitative way that supergranule does? And so why don't we see it on the surface in magnetism?
Because the flows are so much weaker. These are, 10, 20 meter a second flows. Supergranules are 500 meters a second. So supergranules are much, much more powerful. And so they take magnetic elements and form the network. They take it to the edge, and the network forms, in the convergence zones around the edge. And they evolve fairly rapidly. So they're shuffling the magnetic elements around much more efficiently than these guys. They're still the tortoise and hare sort of bit. The supergranules are the hare moving things around really fast, whereas these are very slowly but consistently moving in the same direction.
So couldn't you use the same argument to say that supergranules shouldn't exist because of granules?
No, for the same reason I mentioned earlier, that as you go down, the downflows that you see at the edge of each granule, you go down a little bit below, they start to converge, and you get more downflows converging, and you make these columnar downflows that are on a much bigger scale than the granules, and there has to be upflows associated with them, and so.
The reason I bring this up is because Mark Rast has an idea that all the surface phenomena are related to the fact that it's a very narrow, basically layer in which radiation and the loss of radiation dominates absolutely everything, and the rest is a simple response to that.
See, he still believes that? No. I bring that up because this is an idea he had at least 15 years ago, if not more.
He's still trying to disprove it, I think.
Oh, really?
Yeah.
Are you his agent?
His agent, yes.
I mentioned 000. Anyway, I just wanted to throw a bit of entertainment into the discussion.
Yeah, but as I showed in some of the plots here, the fact that when I do a Fourier transform in space of the supergranule pattern, so I get what the different components are as a function of wave number. How fast are they rotating? They are rotating at rates at a depth equal to their width, which argues very much against the little plane case. It has things aspect ratio 1 between the width and the depth of these things.
So I would argue that that's not convection, because if you look at thermal convection, you have the transport is carried by the temperature gradient, and you have, the pressure gradient, you have an alpha of about 2, meaning that the upwelling cell loses its identity with a mixing length of twice the pressure scale height, which is much smaller than what he's talking about. So it can't be that kind of convection, can it? I don't know.
Well, certainly right at the surface, the pressure scale height's like 100 kilometers.
Yeah, right,
Granules defy your very thing. They're 1,000 kilometers across.
Granule is not convection, it's a surface phenomenon. It's not a thermal convection. It's a loss of energy in a terribly narrow layer because of the because of the thermodynamics of the plasma there.
Yeah,
Suddenly get all this.
I think at this point there's a half a dozen different groups around the planet that are doing radiation hydrodynamic and convection near the surface that would argue otherwise. that would say this is convection.
I think it's all driven by the radiation.
Oh yeah. Oh no, I agree with that. It's the radiation cooling that drives it, but it's
the thermal convection that results
they're still transporting heat.
criterion, but by a surplus loss of energy. That's what it is. Sorry, I'm not being very clear because for some reason I'm going deaf today. I can hear my voice much louder than anybody else's.
No, we hear you fine.
Sorry?
You're closer to the source.
All right, if I can shut down Phil now, are there any other questions?
I shut myself down.
I guess in this work and also the Rossby wave work, these large things are seen in correlation tracking. So why wouldn't they be seen in the spherical harmonic, the power spectra as well?
There's so many noisy things that come in, and again, Thibault and I tried this with the HMI data to look, just take the spherical harmonic spectrum, look at the low wave number and there's still crap down there. I showed you the artifacts that we removed. There's still crap down there that is bigger, much bigger than these flows. And so it's hard to do it with a simple spherical harmonic transform of the Doppler velocity pattern, for instance, because of the noisy junk that's in there.
Could it ever be averaged out? Or?
It might be. A clever student might figure this out.
So I think in interest of time, we should maybe anyone who wants to have questions can talk.
We ask you to put your spherical movie back on as we admire it further.
I was ready.
One final thing. Lisa was going to organize a dinner tonight, so if anyone would like to go, please talk to her. Thank you.
Yeah. All right, thank you. Thank you.